Water drips from newly exposed rock faces, and heavy machinery roars overhead. This triangle crater, now a muddy hollow, will soon be the gateway to one of the U.S.'s most significant rail infrastructure projects. The Gateway program's $16 billion Hudson Tunnel Project, or HTP, would create 2 new rail lines beneath the Hudson River and into Manhattan, ushering in a new age of Northeast Corridor train travel. To understand the scope of this project, it's important to look back at the region's rail issues. A pair of century-old tubes connect New Jersey to Penn Station in Midtown Manhattan, carrying 200,000 passengers daily, 80,000 on New Jersey Transit. These 1910 2-track North River tunnels have endured a century. Salt, seasonal temperature changes, and, most notably, Hurricane Sandy flooding in 2012 have damaged the old tubes. Corroded wiring and disintegrating concrete slow trains on the nation's busiest passenger rail route, infuriating travelers. That frustration has not been limited to the daily workforce. When trains are delayed here, ripple effects are felt up and down the eastern seaboard, from Washington, D.C. to Boston, since this corridor is the busiest in America. It's a sobering reminder of how deeply critical these tunnels are to the economic heartbeat of the Northeast. A single mechanical hiccup, a small crack in the concrete, or a stuck train door can grind traffic to a halt. Given these stakes, the newly launched Gateway program isn't just about building more infrastructure and securing the nation's transportation future. For decades, transportation planners dreamed of an additional Hudson River tunnel. It was a theoretical fix to an ever-growing problem: how to handle the surging passenger loads into Manhattan. That vision remained elusive, buried under budget constraints and political disagreements. In 2010, then New Jersey Governor Chris Christie canceled the access to the region's core, or ARC project, a $8.7 billion plan to build much the same pair of tunnels. The decision sparked controversies, but in the end, the portion of the tunnel leading from North Bergen under Tunnel Avenue was left abandoned, half begun, half forgotten. Fast forward to late 2023, and that very site is buzzing with construction crews once again. Now, under the banner of the Hudson Tunnel Project, workers have cleared out the remnants of the old ARC plan and begun excavating what John Schweppenheiser, the third senior vice president at Knight Consulting Group, calls the gateway to the gateway. Before digging, workmen must remove vestiges of the ARC project. ARC's concrete casings and partially completed substructures must be carefully excavated to build new tunnels. Stabilizing the Hudson River's fragile soils is a crucial Hudson Tunnel Project preparation. Engineers expect much of the new tunnel alignment to go through mud, silt, and other loose materials. TBM entanglement in debris, earth collapse, and water inflows are all dangers from these geologic circumstances. Thus, the Hudson River Ground Stabilization Project injects reinforcing chemicals and removes significant impediments. The idea is to form a more cohesive earth block that can endure digging without damaging the river. Reducing unknowns requires extensive geotechnical investigations, drilling test boreholes, evaluating soil and rock samples, and mapping subsurface conditions. The relocation or protection of water mains, sewer lines, electrical cables, and communication conduits in this highly built area is crucial. Engineers carefully arrange utility diversions and provide strong support mechanisms to prevent outages and hazards. Advanced TBMs for rock and soft soils are essential to building. These machines weigh hundreds of tons and have cutter heads with disc cutters or ripper teeth that break rock. Slurry TBMs, or EPB shield machines, excel in wet or unstable soils. They add bentonite slurry or adjust internal pressure using a screw conveyor. This method stabilizes faces and controls groundwater intrusion. These solutions prevent disastrous blowouts and enormous water inflows for projects beneath rivers like the Hudson. Unlike dirt, a constant rock stratum is more predictable. After excavation, rock provides a sturdy tunnel that requires less reinforcement than softer materials. Engineers anchor freshly exposed surfaces using rock bolts, wire mesh, and shotcrete to avoid tiny rock falls or arch fractures. Some portions of the Palisades have 280 feet of overburden above the tunnel crown. That puts significant geostatic strain on TBM. However, deep tunnels benefit from less broken and more cohesive rock below surface weathering. Engineers may regulate excavation by choosing the right TBM type and using precise boring settings. Geological mapping before the drill helps predict rock-type transitions and natural fault zones. Unlike the Palisades, clay, silt, and debris make up the Hudson Riverbed. Ground freezing or chemical grouting may be used in soft ground tunneling to stabilize soil around TBMs. Cold brine travels through pipes in the soil to generate a temporary ice wall that retains the earth. Chemical grouting solidifies soils with resins or cement. Both methods are utilized with slurry or EPB TBMs to prevent ground collapse and water ingress during tunnel excavation. The Hudson River has seen shipwrecks, cable installations, and industrial dumps. An undersea cable or massive metallic debris might jam the cutter head, halting development for days and requiring costly repairs. Geophysical surveys and diver checks lower risk. Large impediments are removed by cranes or dredging before TBMs arrive. Local, state, and federal environmental rules prohibit tunnel construction from harming Hudson River aquatic life or water quality. To monitor water quality and limit sediment dispersion, contractors use turbidity curtains. TBM slurry is handled via closed-loop systems to prevent unintentional discharges. The engineering needs of a big infrastructure project and the ecological needs of a major river must be balanced with careful planning, real-time monitoring, and contingency plans. A strong granite bulkhead has protected Manhattan's waterfront since the 19th century. The city is protected from erosion and ocean activities by this structure, from Battery Park to 59th Street. Tunneling through is difficult. Contractors must map its thickness and structural condition before designing a staged excavation strategy that may involve controlled blasting or mechanical braking to avoid damaging the bulkhead or other infrastructure. After passing the bulkhead, the tunnels must navigate utilities, foundation piles, and subsurface buildings to reach Penn Station. Building information modeling, ground-penetrating radar, and 3D laser scanning help engineers locate key obstacles. This collaboration requires preventing interference with subway lines, building foundations, and electricity conduits. The new tunnels blend perfectly with a concrete casing under Manhattan's west side, making Penn Station trains arrive smoothly. The TBM quickly installs precast concrete tunnel shells as it cuts through rock or dirt. Rings with wedge-shaped segments are typically used to produce these parts. High-tension fasteners connect waterproof portions. Edge gaskets or sealants prevent groundwater seepage. Engineers use corrosion-resistant stainless steel or epoxy-coated rebar in key areas due to seawater intrusion, pressure variations, and high train traffic. Sumps, pump stations, and drainage canals catch leaks. Authorities monitor tunnel conditions during their estimated 100-year service life using inspection lanes and integrated sensors. Modern train tunnels need good ventilation for air quality and fires. Engineers design fans, ducts, and air shafts with fast smoke evacuation. Normal ventilation systems remove diesel-powered maintenance vehicles or emergency generator exhaust, keeping tunnel air fresh for workers and passenger evacuations. Trains will be powered by overhead catenary lines or a third rail system in the new tunnels. Positive train control and automated safety technologies require signal system upgrades. Backup systems assure train spacing and operations if one system fails. Cable trays, lights, fiber optic lines, and communication networks connect tunnel walls and maintenance-friendly conduits. Tunnels need water mist systems and hydrant lines at intervals for fire suppression in addition to ventilation. Emergency escape to the next tunnel is possible through cross passages between the twin tubes. These routes must be waterproof, fire-rated, and accessible to first responders. Slope, drainage, and sealing must be precise, especially under a river where water penetration might endanger safety. After the new tunnels open, the 1910 tubes will each close in turn for a complete overhaul. Crews will use laser scans to spot fractures, X-rays to check rebar integrity, and moisture sensors to locate hidden leaks, guiding repairs to the lining, track bed, wiring, and drainage systems. Modern shotcrete, corrosion-resistant anchors, and upgraded waterproofing membranes will strengthen these century-old structures, while fiber optics and advanced monitoring replace outdated electrical and signaling setups. In tandem with the tunnel work, The 110-year-old failure-prone swing bridge over the Hackensack River is being replaced by a new fixed-span Portal North Bridge. Its robust design and advanced switching technologies will boost rail capacity and cut delays. Penn Station and Secaucus Junction expansions also mean reworked track interlockings, improved ventilation, and wider platforms, ensuring smooth integration with the new tunnels. The region will have 4 functional Hudson tracks when the new tunnels open and the existing ones return after refurbishment. This will greatly increase capacity and redundancy. Rail operations can continue if one tunnel needs maintenance, the result of years of analysis, design, and invention for engineers. One of the most complicated train projects in U.S. history will showcase modern TBM technology, geotechnical knowledge, and structural engineering. These cutting-edge methods, ground freezing, slurry TBMs, and real-time instrumentation may influence future tunnel construction nationwide. As other cities witness New York's success, they may use similar methods for expansions or repairs, igniting a rail infrastructure renaissance in America. At peak construction, the Hudson Tunnel Project will employ 7,500 civil and structural engineers, heavy equipment operators, and surveyors. To provide a trained workforce, TBM operation, steel erection, and advanced welding training programs are essential. The initiative might help improve tunnel construction workforce education, aiding other large-scale infrastructure projects nationwide. The $16 billion Hudson Tunnel Project proves just how powerful engineering can be in tackling our biggest infrastructure challenges. Despite funding and political hurdles, a dedicated team of engineers, geologists, and builders is pushing forward, using chemical grouts to stabilize Hudson's muddy bed, drilling through the Palisades' solid diabase, and threading sleek new tunnels into a jam-packed Midtown Manhattan. If you enjoyed this look at the Hudson Tunnel Project, hit that like button, subscribe, and follow our channel for more big build stories from around the world.